Hi again, year 10, 11. We're still looking at exercise 10G, where we're looking at events that depend on another event, so complementary events. But what I wanted to have a look at also is events that are independent. And we say that events are independent if those two events don't depend on one another. So we can actually have a look at the rule that we've been looking at and see how that would apply to proving or deciding if an event was independent or not. So what we've been looking at during this topic is we've been looking at this rule here, okay, where A is what we're going to be finding, the probability of A, given some other information. And what we've said that the probability of A, given this other information B, is found by finding the probability of A and B over the probability of B. Okay. But what we can say is if our events A and B are independent of one another, or the fact that finding the probability of A doesn't depend on B, what we would find at is that our probability of A given B would be equal to the probability of A, in that it does not depend on B. B is independent of A. That would tell us the two events are independent. So I want to show you the working through an exercise where we can actually look at using this formula, and I might just put the last part in blue as well, and deciding, well, hey, what does our formula equal? Does our probability of A given B equal this one here? Does it equal our first one that we've looked at? In that case, the events A and B depend on one another. Or does our probability of A given B equal the probability of A? In which case that would show independence, that A and B were independent of one another. And that's what we want to have a look at now. The question I'm going to work through is this one. It is in your textbook in chapter 10, but exercise G. It's not in your notebook, but it will be in this OneNote. So I want to work through this. It's fairly long, but I want you to flow through and follow through with me. Okay, so in this example, two dice are thrown, one after the other. Let's fix that up. Okay, so let A be the event. The first dice shows an odd number. Let B be the event. The second die shows the number 1, 2, or 3. And let C be the event. The number is 5. Okay, now let's need to think about this a bit. Although we have 3 events we're looking at, those are not the things that we are doing. The things that we are doing are we are throwing the dice. We are throwing a first dice and recording its values, and we are throwing a second dice. The things that we're looking for, or the events, are the numbers, the odd numbers, the numbers 1, 2, and 3, and the sum. Okay, so what I've done is popped a table down below which shows the values that we would get in throwing our first dice and our second dice. You could also use a tree diagram for this. It would be messy, so I've chosen to do it this way. This is the way I did it in exercise 10B, but if you like, you could do a tree diagram instead, whichever way you like. Let's have a look at the first question. Well, let's have a look at the question. The question is saying which pair of events are independent. So we need to look at A and B. We need to have a look at B and C. We need to have a look at C and A. That's our pairs of events. Now, if we're showing independence or dependence, we're going to have a look at what I've just talked about at the start. We're going to have a look at A given B, B given C, and C given A. Work out what we get as our answer, and then we're also going to work out the probability of A, B, and C, and see if this one is equal to this one here. Okay, if they are, then our events will be independent. If they're not, then they will depend on one another, and that's what we're going to work through now. Okay, so the first thing I want to have a look at is the probability of A. A is the event that the first dice shows an odd number. Okay, so our first dice is shown along the top, and our first dice in the table is represented by our first number here. So the first dice showing an odd number would be 1, 3, and 5. We've got 6 down and 3 across, so we're going to have 6 times 3 is 18. We're going to have it occurring 18 times. And all up, we have 36 different possibilities. Of course, we've got 6 across and 6 down gives us 36. So we've got 18 over 36. And that equals 1/2. So the probability of A is 1/2. Next, we want to have a look at the probability of B. Now, what's B? B is the event that the second die shows the numbers 1, 2, or 3. Okay, so have a look at our diagram. The second dice is along here, shows a number 1 at the second number, 2 at the second number, or 3 at the second number. So that's also 6 times 3, which is 18. So we've also got 18 out of 36 possibilities, which also equals 1/2. The probability of C now. What event is C? C is the event that the sum is 5. So we need to have a look for where our sum is 5. That should fall out really nice and easily. It's going to be a diagonal. 4 and 1 is 5. 3 and 2 is 5. 2 and 3 is 5. And 1 and 4 is 5. Nowhere else in there are we going to end up with a total of 5. So that gives us 4 out of 36. Either in your head or in your calculator, pop that in and you end up with 1/9. Okay, the next things we want to have a look at are finding the probability of A and B, the probability of B and C, and the probability of C and A. Okay, so the probability of A and B is going to be what is in both A and in both C, remembering that that and is our intersection. So it's in both of those. So A and B would be that the first number shows an odd number and the second number is 1, 2, or 3. So if we have a look through there, that the first number is an odd number is going to be in our columns 1, 3, and 5. And that the second number is a 1, 2, or 3. That would cross over there with our 1 across here, 2 across here, and 3 across here. So looking at the numbers in our intersection, we end up with 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. We end up with 9 out of 36. Popping that one into your calculator, you'll break that down to 1/4. Okay, let's have a look at the next one. B and C. So we're looking here for the intersection between B and C, and that is that the second die shows the number 1, 2, or 3. So here's our second die, and here's our 1, 2s, or 3s. And that the sum is 5. That would only occur 3 times. It would be over here, and over here. So we would get 3 out of 36. For that one, you should be able to do that one in your head, but 3 over 36 breaks down to 1/12. We're nearly there. We're looking now for events the probability of C and A. So where C and A intersect, so we will be looking for the summing of 5, and A is the first die shows an odd number. The summing of 5 is our blue ones here, but our odd numbers are on the first dice are going to be 1, 3, and 5. So we've only got 2 in there that overlap into both of those groups. 2 out of 36, which is 1/18. So now we've done that, you probably need to have a look at what are we actually testing. So let's go back and have a look at the question again. Okay, we've looked at our diagram, we've looked at A, B's and C's. Oh, there we are. We're looking at which pair of events are independent. Do you remember how to do that? Remember what we're going to look at? And we've got to decide whether or not our probability of A given B equals our probability of A and B over our probability of B. And does it also equal the probability of A? And we're going to do that for the other 2 events as well. So let's look at that first. Let's look at the first one. The probability of A given B is equal to our probability of A and B over our probability of B. Let's swap our values into that. So our probability of A and B is 1/4. Our probability of B down here is 1/2. Let's see what that equals. Okay, that equals a half. But let's have a look at that. Does that also equal the probability of A? Let's go over and see. It does. The probability of A is also a half. So what we've shown is that the probability of A given B, working through our formula that we've been working through, gives us a half, but it also happens to equal the probability of A. So what we would say then is, therefore, events A and B are independent. Okay, we can do that again for the next two events to decide if they are independent as well. So we can work out the probability of B given C. And we'll pop that in as our probability of B and C over our probability of our probability of C. Our probability of B and C is 1/12 divided by our probability of C, which we've got over there as 1/9. And that is equal to 3/4. Does that equal our probability of B? Let's go and have a look. Our probability of B is 1/2. It does not equal our probability of B. So therefore we'd say events B and C are not independent. I think you're probably getting the hang of this now. But likewise, we can look at the other pair of events, which are C given A. That would be the probability of C and A, or A and C, over the probability of A. So the probability of C and A, we worked out to be 1/18. Our probability of A, we worked out to be 1/2. Let's see what that equals. Okay, popping that in your calculator or in your head, that equals 1/9. We're going to check to see if that equals our probability of C. Does our probability of C equal 1/9? Yes, it does. We've worked that one out, so it does. So therefore, events A and C are independent. Okay, another thing I would like you to have a look at is what happens if we arrange this rule, our probability of A given B. So I've written the rule down that we've been working with. And it states the probability of A given B equals the probability of A and B over the probability of B. Now, let's rearrange it. Let's multiply both sides by the probability of B. And what we'll end up with is that the probability of A given B times the probability of B is equal to the probability of A and B. We've multiplied by the right, we've multiplied by the left, the rights have cancelled out, and that's what we've ended up with. Okay, let's have a think about what else that is telling us. So remember from the last question, we know that the probability of A given B equals the probability of A if A and B are independent events. So when they have nothing that relies on the other. So what I could do is I could substitute in my probability of A into where my probability of B is. What I will end up with is that my probability of A times my probability of B will be equal to my probability of A and B. Now have a look at that rule that I've just written. I'm going to highlight it. Does that look familiar? I'm hoping it looks familiar. If it doesn't, follow me now. I'm going to go back up from 10G back to 10E. Okay, and we have a look at multi-stage events. And I said in there that the probability of AB, or A and B, was equal to the probability of A times the probability of B. And that's basically what's happening when we're multiplying across the arms of our tree diagram. So you've seen that before. Now you've seen it down here as well, if A and B are independent.